Welcome to Lesson 6.3 Advanced LoRa Techniques. Overview, File New NEC. Overview. In this lesson, you're going to master 4 cutting-edge LoRa variants. QLoRa for memory efficiency, DORA for better accuracy, LoRa Plus for faster convergence, and LoRa for adaptive rank allocation. By the end, you'll know exactly when to reach for each one and how to combine them for maximum performance. This is a 90-minute advanced lesson, so buckle in. Learning objectives. Here's what you'll walk away with. A clear understanding of QLoRa, DORA, LoRa Plus, and LoRa, not just what they are, but when each one earns its place. You'll implement all 4 techniques hands-on, learn how to combine them strategically, and realistically expect 5 to 10% accuracy improvements over a standard LoRa baseline. LoRa variance comparison. Fauna variance comparison. You'll master these techniques quickly. Fauna variance comparison. Fauna variance comparison. Before writing a single line of code, it's worth orienting yourself across all 4 techniques at once. Standard LoRa is your baseline. Medium memory, fast, good quality. QLoRa adds 4-bit quantization to slash memory while keeping quality nearly identical, making it the go-to for limited VRAM. DORA decomposes weight updates into magnitude and direction separately, which costs you a bit of memory and speed, but delivers the best quality of the group. LoRa Plus uses asymmetric learning rates across the adapter matrices, no extra memory, noticeably faster convergence, and LoRa dynamically allocates rank where it matters most, slower and more complex, but highly parameter efficient. Each technique occupies a different point in the trade-off space. Your job is to know which point matches your constraints. Technique 1. QLoRa, Quantized LoRa. QLoRa's core innovation is pairing 4-bit quantization of the base model with full precision LoRa adapters. Here's how the memory math works out in practice. The strategy has 3 moving parts. First, the base model is loaded in 4-bit precision. A 7B parameter model drops from roughly 14 GB down to about 4 GB. That's not a rounding error. That's the difference between fitting on your hardware and not. Second, the LoRa adapters themselves stay in full precision, which is where the actual learning happens. You don't want to quantize that. Third, during the forward pass, the quantized weights are dequantized on the fly. The model computes as if it has full precision weights, but stores them compressed. You get the memory savings of 4-bit storage with the numerical stability of full precision computation. That's the elegant trick at the heart of QLoRa. The practical payoff is significant. You can train a 7B model where you'd otherwise only fit a 3B. VRAM drops from 6 to 8 GB down to 3 to 4 GB. Quality is nearly indistinguishable from full precision LoRa. And here's the thing. If you've been following this course, you're already using QLoRa. It's Unslot's default. You've been getting these benefits from day one. Here's the code that puts QLoRa into action. The right single quote fastlanguagemodel.frm underscore preprenade right single quote call loads right single quote unslot slash llama-3.2-3b-instruct right single quote with load underscore in underscore 4-bit. Then getPeft model wraps the model with your LoRa configuration, rank, alpha, dropout, and target modules. Notice the print statements at the end. They confirm QLoRa is active and report current GPU memory allocation in gigabytes. That memory number is your sanity check. If it looks unexpectedly high, something in your environment is holding onto a previous allocation, and you'll want to restart the kernel before training. The key insight here: QLoRa isn't a special mode you opt into. It's the baseline you've been working from. Every lesson in this course has been running on top of it. The memory savings scale impressively with model size. A 3B model shrinks from 6 GB to 2 GB, a 67% reduction. A 7B model goes from 14 GB to 4 GB. A 13B model from 26 GB to 7 GB. And a 70B model, which would require 140 GB in 16-bit, fits in 35 GB with LoRa. With your 2 Tesla P40s giving you 48 GB of total VRAM, that puts models up to around 30 billion parameters within reach. That's a remarkable amount of capability sitting on your workstation. Technique 2. LoRA, weight decomposed LoRa. LoRa's innovation is conceptually elegant. Instead of treating a weight update as a single undifferentiated matrix, it decomposes that update into two separate components, magnitude and direction, and trains them independently. Here's what the math looks like. Standard LoRa updates weights as W equals W0 plus BA. The low-rank product BA gets added directly to the frozen base weights. Simple and effective, but magnitude and direction are coupled. You can't control one without affecting the other. LoRa introduces a learned scalar M that scales the normalized direction of W0 plus BA. That normalization step, dividing by the norm, isolates the directional component. The scalar M then controls magnitude independently. What this buys you in practice is more stable gradient flow during training. The model can adjust how much it changes a weight separately from which direction it changes it, which leads to better learning dynamics and measurably improved final accuracy. The trade-off is real but manageable. LoRa typically delivers 2 to 5% lower loss compared to standard LoRa, with more stable training curves. The cost is roughly 10% more memory and about 15% slower training. If accuracy is your primary objective and you have VRAM headroom, which you do with 48 GB across your 2P40S, LoRa is worth serious consideration. Enabling LoRa in code requires exactly one additional flag. After loading the model with write single quote fast language model .from underscore preprint write single quote comma, the LoRa config takes use underscore do. The confirmation print shows LoRa is active and the trainable parameter count tells you what fraction of the model you're actually updating. For a 3B model with typical LoRa settings, expect somewhere around 0.5 to 2% of total parameters to be trainable. That's the efficiency of LoRa, a tiny fraction of parameters doing the heavy lifting. This benchmark script puts LoRa and LoRa head-to-head under identical conditions. It loads the same base model, configures each variant with matching hyperparameters, trains on the same dataset for the same number of epochs, and records final loss, training time, and peak memory usage. The use LoRa flag is the only variable that changes between runs. Running this on your own data before committing to LoRa for a production fine-tune is exactly the right workflow. The performance delta varies by task, and you want empirical evidence, not just general guidance. What the benchmark typically reveals: LoRa achieves 2 to 5% lower final loss, uses 10 to 20% more memory, and takes 15 to 20% longer to train. The decision rule is straightforward. Reach for LoRa when accuracy is the primary metric and you have the memory budget to absorb the overhead. Technique 3. LoRa Plus. Improved learning rates. LoRa Plus makes a subtle but high-impact observation about the two matrices inside every LoRa adapter. The A matrix and B matrix play fundamentally different roles, yet standard LoRa trains them with the same learning rate. LoRa Plus argues that's leaving performance on the table. In standard LoRa, both the A and B matrices train at the same learning rate, say 2E4. LoRa Plus breaks that symmetry. The A matrix keeps the base learning rate, but the B matrix trains at a rate 16 times higher, 3.2E-3 in this example. The reasoning is grounded in the initialization. A is initialized randomly and B starts at 0, so B needs to move faster early in training to establish meaningful weight updates. By letting B learn at a higher rate, the adapter converges to a useful representation in roughly half the training steps. Same final accuracy, twice the convergence speed, no extra memory. That's an unusually clean win. The benefits are hard to argue with. Approximately 2x faster convergence, equal or better final accuracy, zero additional memory cost, and a straightforward implementation. For anyone running long training jobs on constrained hardware, cutting the required steps in half is a meaningful practical advantage. The implementation requires a custom optimizer that separates model parameters into three groups: LoRa A matrices, LoRa B matrices, and everything else. The get underscore LoRa plus underscore optimizer function handles this separation, assigning the higher learning rate to the B group and the base rate to A. The print output confirms the parameter count in each group and their respective learning rates. Verify these numbers before starting a training run. If the B group learning rate isn't 16x the A group rate, the asymmetry isn't active and you're just running standard LoRa with extra steps. Rather than wiring up the custom optimizer manually every time, you can encapsulate it in a LoRa plus trainer class that extends Hugging Face's standard trainer. The only method you need to override is create underscore optimizer, which calls get underscore LoRa plus underscore optimizer with your base learning rate and ratio. Set base underscore LR to 2E4 and ratio to 16. From that point, the trainer behaves identically to the standard trainer. Pass in your model training arguments and dataset, call write single quote trainer.train SSE, and the asymmetric learning rates work automatically on every update step. Technique 4. Add a LoRa, adaptive rank. Standard LoRa applies the same rank to every adapted module, which means you're spending the same parameter budget on attention projections and feed-forward layers regardless of how much each one actually needs to change. LoRa challenges that assumption by learning which modules deserve more capacity and allocating rank accordingly. With standard LoRa, every module gets rank 16, query, key, value projections, gate projections, everything treated equally. Ada LoRa starts with an initial rank and then redistributes capacity during training based on importance scores. Attention projections Q underscore proj, K underscore proj, V underscore proj tend to be assigned higher ranks, around 24, because they're central to how the model processes relationships. Feed-forward projections like gate underscore proj and down underscore proj typically settle at lower ranks, around 8 to 12, because they contribute less to task-specific adaptation. The model figures this out automatically. You set the budget, Ada LoRa decides how to spend it. The payoff is genuine parameter efficiency. 3 to 7% accuracy improvement using the same total number of trainable parameters as standard LoRa. The cost is real, training is slower, and the configuration is more complex. Ada LoRa makes the most sense in research contexts where you're exploring what a model can learn, or in production scenarios where parameter efficiency is a hard constraint. Setting up Ada LoRa uses Ada LoRa config instead of the standard LoRa config. The three rank parameters are the ones to understand. R sets the maximum rank any module can reach. Init underscore R is where all modules start, and target underscore R is the average rank the algorithm drives toward as it redistributes capacity. After wrapping with get underscore peft underscore model, the model begins training with uniform ranks and progressively reassigns them based on gradient information. After training completes, inspect the learned ranks per module. That output tells you exactly which parts of the model the task actually relied on, which is genuinely useful information for future experiments. The learned rank output after a LoRA training is more than a confirmation that the technique ran, it's a diagnostic. High rank modules like v_proj at rank 20 are the ones the model determined were most critical for the task. Low rank modules like gate_proj at rank 8 contributed less. If the distribution looks flat, everything near the same rank, our LoRA didn't find meaningful variation, which suggests either the task doesn't require differentiated capacity or the training ran too few steps for the rank allocation to converge. A healthy LoRA run shows clear rank differentiation across module types. Best practices: when to use each. Here's the decision framework distilled into clear priorities. If VRAM is your binding constraint, LoRA is already active by default, nothing to change. If maximum accuracy is the goal and you have memory headroom, LoRA gives you 2 to 5%. If memory is tight but you still want an accuracy edge, LoRA delivers 3 to 7% within the same parameter budget. If speed is the priority, LoRa Plus halves your convergence time at no memory cost. And if you want the best combination of quality and speed, LoRa plus LoRa Plus together is the strongest pairing in the toolkit. With 48 GB of VRAM across your 2P40S, you're not particularly memory constrained for most 3B to 7B models, which means you can afford to experiment with the higher quality options. With 48 GB of total VRAM across your 2 Tesla P40S, here are 3 concrete configurations ranked by use case. Configuration 1 is the balanced recommendation. The balanced configuration combines LoRa and LoRa Plus, the best memory efficiency paired with the fastest convergence. Load the model with load_in_4-bit =true. Apply LoRa at rank 16 with get_peft_model. Then create the optimizer with get_LoRa plus_optimizer. This setup gives you the 4-bit memory savings of LoRa plus the 2x convergence speed of LoRa Plus with no accuracy penalty compared to standard LoRa. For most fine-tuning tasks where you want reliable results without long training runs, this is the configuration to start with. Configuration 2 is the maximum accuracy setup, LoRa plus DORA plus LoRa Plus. Load in 4-bit, enable use_DORA =true in the LoRa config, wrap with get_pef_model, then apply the LoRa Plus optimizer. You're stacking 3 improvements simultaneously. LoRa keeps memory efficient, DORA improves the quality of each weight update, and LoRa Plus accelerates convergence. Expect roughly 10 to 20% more memory and 15 to 20% longer training compared to configuration 1 in exchange for the best accuracy this toolkit can deliver. Configuration 3 is for research and experimentation. The research configuration uses LoRA, which is the right tool when you want the model to tell you something, specifically which modules matter for your task. Load in 4-bit, then create an LoRa config with r=16 as the maximum rank, init_r=12 as the starting rank, and target_r=8 as the During training, LoRa will progressively redistribute rank capacity toward the modules that contribute most to reducing loss. After training, inspect the per module ranks. That distribution is empirical evidence about your model's learning dynamics on your specific task, and it's genuinely informative for designing future experiments. Comprehensive comparison experiment. This experiment script runs all variants back to back under controlled conditions. It defines a set of configurations: standard LoRa, LoRa, DORA, LoRa Plus, LoRa, and combinations, then iterates through each one, trains the model, and records accuracy, final loss, training time, and peak memory usage. Results are collected into a pandas data frame sorted by accuracy and printed in a clean table with the winner highlighted. Running this on your actual target dataset before committing to a production fine-tune is the right approach. The performance rankings are task dependent. What wins on one dataset won't necessarily win on another, and 20 minutes of benchmarking can save you hours of training the wrong configuration. The comparison table gives you everything you need to make an informed decision. Each row shows a different variant with its final loss, accuracy, training time, memory usage, and trainable parameter count. In a typical run on instruction following data, LoRA plus LoRA plus emerges as the winner, around 89.2% accuracy at 18.5 minutes of training time. What the table also reveals is the shape of the trade-offs. Pure ADA LoRA might match DORA on accuracy, but takes significantly longer. Standard LoRA trains fastest, but leaves accuracy on the table. Read the full table, not just the winner row. The second best option for your specific constraints might be a better practical choice than the absolute accuracy champion. Advanced LoRA checklist. Key takeaways. 7 things to carry forward from this lesson. First, LoRA. You've been using it the whole time. It's the 4-bit quantization foundation everything else builds on. Second, DORA adds 2 to 5% accuracy by decomposing weight updates into magnitude and direction at a modest memory and speed cost. Third, LoRA plus doubles convergent speed by applying asymmetric learning rates to the A and B matrices. No extra memory, no accuracy penalty. Fourth, ADA LoRA learns optimal rank allocation automatically, delivering 3 to 7% efficiency gains. Fifth, the strongest combination is DORA plus LoRA plus best quality, best speed, fits comfortably in your 48 GBs. Sixth, the right choice depends on your actual priority, memory, quality, or speed. There's no universal winner. And seventh, benchmark on your data. These numbers are representative, not guaranteed. Your task will have its own answer. What's next? You now have a complete toolkit for advanced LoRA. Not just the mechanics, but the judgment to choose the right variant for any situation. The next step is domain adaptation, taking a general purpose model and specializing it deeply for a specific field or knowledge domain. That's lesson 6.4, continued pre-training. Additional resources. The original papers for each technique are worth reading if you want to go deeper. The LoRA paper, the DORA paper, the LoRA Plus paper, and the ADA LoRA paper. The Hugging Face PFS library documentation ties them all together from an implementation standpoint. Your LoRA knowledge is now at expert level. The next frontier is specialization. This chart illustrates 2 important relationships you need to internalize before choosing a LoRA rank. On the left, validation perplexity drops as rank increases. The model gets better as you give the adapter more capacity. But notice the curve flattens sharply around rank 32. Beyond that point, you're paying more in compute and memory for diminishing accuracy returns. On the right, training time scales roughly linearly with rank. Rank 64 doesn't just cost twice as much as rank 32. It costs twice as much for a fraction of the quality gain. The practical takeaway, rank 16 to 32 is the sweet spot for most tasks. Start at 16, benchmark, and only push higher if the accuracy delta justifies the cost. Not all target modules contribute equally, and knowing which ones to prioritize will sharpen every fine-tuning decision you make. The attention projections Q_proj, K_proj, and V_proj are high impact and should be included. The output projection O_proj is also high impact and particularly valuable for instruction following tasks. Moving into the feed-forward network, gate_proj and up_proj are medium impact and most useful when the task involves factory down_pros in the same category. At the bottom of the priority list are embed_tokens and lm_head, low impact for most tasks, but worth including selectively when you're adapting vocabulary or working with a specialized tokenizer. When in doubt, start with the attention projections and add feed-forward modules if accuracy plateaus. This three-axis comparison, memory efficiency, quality score, and training speed give you an honest picture of where each LoRa variant sits in the trade-off space. LoRa consistently holds strong quality scores across the comparison, confirming its reputation as the accuracy-focused choice. LoRa Plus and Galore lead on training speed, which aligns with the convergence improvements we covered. QLoRa's memory profile reflects the 4-bit compression savings. What the chart reinforces is that no single variant dominates all 3 dimensions simultaneously. Every choice involves a trade-off. Map your own constraints onto these axes. If memory is your bottleneck, optimize for that bar. If you're running time-constrained experiments, optimize for speed. The chart is a navigation tool, not a ranking. After fine-tuning, merging the LoRa adapter back into the base model is often the right move before deployment. Here's why it matters and how it works. During training, the base model weights W0 stay frozen and the adapter matrices A and B accumulate the learned updates. At merge time, you compute W equals W0 plus BA and write that directly into the model weights. The adapter ceases to exist as a separate structure. The result is a single model with no adapter overhead, faster inference, simpler deployment, and full compatibility with serving frameworks like Ollama or GGUF-based tools. The trade-off is that you can no longer swap adapters at inference time. If you need that flexibility, keep the adapters separate. If you're deploying one specialized model and want maximum inference speed, merge it. This diagram makes the LoRa decomposition concrete. In standard LoRa, the weight update ∆W equals BA minus the magnitude and direction are entangled in a single matrix product. You can't increase how much a weight changes without also affecting which direction it changes. LoRa separates these concerns explicitly. The magnitude component, the norm of W0, is trained independently. The directional component V0 is normalized and updated separately via ∆V. This decoupling gives the optimizer more precise control over each weight update. In practice, it produces more stable gradient flow, especially in early training when the adapter is still establishing its representation. That stability is what drives the 2 to 5% accuracy improvement. It's not a free lunch, but the cost in memory and speed is modest relative to the gain. This bar chart compares LoRa variants across quality, parameter count, and speed, all normalized to standard LoRa at 100%. The key observation: LoRa Plus, Vera, and Dora all maintain quality at or above the standard LoRa baseline while varying significantly on the other 2 axes. LoRa Plus improves speed without sacrificing quality. Dora improves quality at a modest speed cost. Vera achieves competitive quality with dramatically fewer parameters. What this chart makes clear is that the variants aren't just incremental tweaks. They represent genuinely different engineering trade-offs. When you're choosing between them, identify your binding constraint first. Quality constrained? Dora. Parameter constrained? Vera or Ada LoRa. Speed constrained? LoRa Plus. Knowing your constraint before choosing your technique is what separates systematic adapter composition is an advanced capability worth understanding even if you don't use it immediately. The idea: you fine-tune separate adapters for different skills, say one for coding style and one for formal tone, then combine them into a single model at inference time. Each adapter contributes proportionally based on its weight: 0.6 for the coding adapter, 0.4 for the formal tone adapter in this example. Two implementation paths exist. Merge underscore and underscore unload SE bakes the weighted combination directly into the model weights. Fast inference, no runtime overhead, but the composition is fixed. Add underscore weighted underscore adapter SE keeps the adapters separate and applies the weighting dynamically. The practical value here is modularity. Train specialized adapters once, then remix them for different deployment scenarios without retraining from scratch.